All right, next is the adrenal gland. And on this picture, it's right there, right on top of the kidneys. The adrenal glands are also called the suprarenal glands because they're on top of the kidneys. Renal means the first kidney. I typically call them adrenal glands. So just simply stated, sit on top of kidneys. Kidneys are by your 12th rib and they're retroperitoneal on your back body wall. We'll talk about kidneys more at the end of the course. So let's just study that gland at the top, the adrenal glands or suprarenal glands. And in your notes you'd have, I kind of drew like on the board previously where you cut through it. You have an inner part and an outer part called the cortex. Okay. Medulla is always the inner part, cortex is always the outer part. It kind of means like bark. Cortex means bark, the outer part. And think of the adrenal gland as a stress response hormone. A stress response hormone that, well, there's long-term stressors and short-term stress responses. So you can categorize stress response in the long term. So think of that as days, weeks, months, okay, a long time. Maybe you're stranded in the forest, overnight for days. Okay, and your survival rate goes down with each passing day. Or we call it the starvation death camp scenario. You're a prisoner of war. Remarkable stress for long periods of time, stranded at sea. Things like that. And those long-term stressors, the adrenal cortex will secrete what are called corticosteroids to help you deal with those. So the long-term secrete corticosteroids, and those come from the cortex, the adrenal cortex, of course. And in the short term, minutes, seconds, hours maybe, hopefully not hours. Maybe like a heart attack, or just you're scared, or even exercise is considered a short-term stress response, okay? Adrenaline going. You secrete catecholamines, epi-norepi. So those come from the adrenal medulla, just medulla for short. So that's kind of why I put this slide together, is to get that in your head. So you have long-term, you have short-term, and the identification. Now this isn't the best looking slide because it's from our collection. You'll see our collection isn't ideal. But even in this kind of messy picture, maybe I could have cleaned it up a little better. Your eyeball should be able to distinguish between cortex and medulla. And I always tell students, try to find that border. Okay, and once you do that, then try to find the outermost capsule. So then you can get all the regions identified on a histology slide. For example, this picture is a little easier to teach from. What we see is that cortex is divided into 3 zones, hence the terms zona. So we'll go through them, but just real quick to teach from the slide. The inner part, number 1, adrenal medulla, choice D. So I'll just go from 4, 3, 2. 4 is the outermost part. That's the Zona Glomerulosa. 3, this faded white part, that's kind of the largest zone of the cortex, is the Zona Fasciculata. And this innermost part of the cortex, which borders the medulla, is the Zona Reticularis. Okay, so right there, Zona Reticularis, this term here. So you are expected to be able to know those zones and what they secrete. And then so here's the picture from your book. And what they do is they have the kidney and the adrenal gland, and notice they put this little box right there. That's kind of like a low magnification under our microscope, which we'll look at later. And they put an illustration next to the histology. Okay, and we'll do the same thing during the lab time today. But for now, let's just kind of note the zones of the cortex. So again, cortex, that's the long-term stress response. But let me erase this. Know the zones. Zona Glomerulosa. Now, if you look at the illustration, the cells are arranged with these oval clumps of cells. Just remember, it's the outermost part. It's not the capsule. Okay? The outermost part is the capsule, but those aren't cells that secrete corticosteroids. It just has a capsular function. These cells are the Zona Glomerulosa. The term comes from the word root glomer. It means ball of yarn, because that's kind of how the cells are arranged. Now, that's not so much important. You got to know Zona Glomerulosa, it's the outermost zone. They secrete mineral corticoids from this zone. And there's only one that you got to know from this class of mineral corticoids. The one you got to know that's a mineral corticoid is aldosterone. We already talked about it. No aldosterone. It's responsible for facilitating sodium reabsorption, if you've forgotten. Okay, this zone here with these cord-like arrangement of cells, it's called the Zona Reticularis. Now the Zona Reticularis, they'll secrete glucocorticoids, regulates blood sugar. And there's only one from this class that you got to know. It's cortisol. Cortisol. More on cortisol later. But right now you know that, okay, the long-term stress response, you want to regulate sodium and blood sugar. Okay. The innermost zone, I usually don't see it this big on our slide, but it's the Zona Reticularis. Again, it's the one that borders the medulla. They secrete the sex hormones. Now, most of the sex hormones come from the gonads, but there are some released from the Zona Reticularis, and we're not sure what the function is. In the adrenal medulla, I already mentioned a couple of times, they secrete epi and norepi. So there's a simple memory jogger you can use to remember their function. Salt, sugar, sex for each zone. You know, referring to the fact that that's what they regulate. The aldosterone, the cortisol, and the sex hormones. And so be able to identify the zones. This is a picture from our collection. And then so I know it's labeled. The question becomes, if it weren't labeled, could you identify the zones? I mean, without a label, could you tell that that's the border between cortex and medulla? Well, we'll look at a slide later today and we'll have some practice. So anyways, this slide just kind of has everything we've just noted for you. Remember, epi and norepi, in the last lecture, I did refer to them as catecholamines. And let's remember that all steroid hormones have this structure, which you got to know. This structure I didn't teach, don't worry about it. But this structure, the important fact that I taught you is that, let me ask you, is this lipid soluble or not? Yes or no, lipid soluble? Yes. So that means they can do the direct gene activation. That's what I talked about last time. This slide, well, don't worry about it. You don't have to memorize this. I do show slides like this that you do have to memorize. You got one coming up, but not this one. I just want you to get a general sense. All steroid hormones are derived from cholesterol. So all the ones you got to know, I kind of put arrows next to them. For example, these are the female sex hormones. Here's are the male sex hormones. Okay. There's cortisol. There's aldosterone. They're all derived from cholesterol. The changes are enzymatic. I think one I'll point out now is this one. Okay, let's write that down. Hold on a second. Let me clear the board. Okay, so I misspelled it. Androstenedione. Sorry. Androstenedione. It's a big long word. That's a male sex hormone. One of the important sex differences between the biological sexes, male and female, is a hormone that's converted from androstenedione, which is male. It's converted by aromatase to estrone. Okay. Estrone is one of the hormones in the class of female hormones called estrogens. And so the other one is testosterone, a male hormone converted by aromatase into estradiol. So both of these are male hormones by this one enzyme converted into female hormones. So those will come up again. That's why I'm doing it now. Well, proceeding on with more of the physiology of the zones, the Zona Glomerulosa is responsible for the secretion of aldosterone. And along with ADH, it'll help increase the blood pressure. We talked about that last time. And go back and look at your notes. It really does regulate sodium reabsorption. But I want to talk about how you stimulate aldosterone's release from the Zona Glomerulosa. And there's one mechanism where you can inhibit it. So that way, if you inhibit aldosterone's release, there's a protein called atrial natriuretic peptide that can be released when blood pressure is too high, so you'll lower it. Because remember, aldosterone helps keep blood pressure high in a stress response. Now, this figure shows you all the ways you control the release of aldosterone. So let me outline it for you. There's 3 mechanisms of release and 1 mechanism of inhibition. So we got it color-coded there. Now, if you look at the figure, recognize the zone. They show it right there, Zona Glomerulosa secreting aldosterone. We know already from last time it targets the kidneys. You get the reabsorption of water, increased blood volume, increased blood pressure. That was covered previously. But now I want to go into all this above it. Okay. So a stimulus for release could be number 1, RAS, R-A-A-S. This mechanism, I'll go into detail in the next slide, but that's one. Okay. Details to come. Secondly, let's go with low sodium. Low sodium levels will facilitate its release because we know that it can cause the reabsorption of sodium. That has a direct stimulating effect to release aldosterone if your blood levels are low. Or it can be controlled hormonally. We learned this morning that if you're under a lot of stress, ACTH stands for adrenocorticotropic hormone. That'll target the adrenal cortex. Okay, so it's under hormonal control. So any of those things will facilitate the release of aldosterone into the bloodstream. The fourth one, which is a inhibiting effect, I'll just put inhibition. ANP. Okay, that comes from the heart, basically. They show a picture of the heart. That's a good place to monitor blood pressure. That peptide, when released, if you drop the level of aldosterone, it should help relieve hypertension or high blood pressure. So that's the only one you got to know as a mechanism of inhibition. So I want to talk about that first one. The R stands for renin. Okay. So let's look at this one. I'm going to erase this. I need the whole board. What we're going to see is that renin and ACE, they're going to cleave different molecules in a cascade that will eventually help bolster blood pressure. So here's the cascade. Oh, sorry, this one. Okay, so this slide, well, let's detail it. I mean, it's pretty busy, but I'm going to take it through step by step. If you just count the numbers, it looks like we got to get to 14, 15 out here. But let's kind of like take a macro view, or why am I teaching this? You're under stress, a drop in blood pressure. You're dehydrated, decreased blood volume, decreased blood pressure. So ultimately, your body needs a mechanism to return it to normal. This is a stress response. Okay. So what it involves, all these things, let's go through it. So you got the 1, 2, 3. Dehydration, number 1. That will lead to decreased blood volume, decreased blood pressure. And that ultimately, the drop in blood pressure, that's the vital thing you want to correct. So they point to 3 to number 4. Number 4 is a picture of kidney, because the kidney will release renin into the bloodstream. That's the first R in RAS. Kidney has a way to detect a drop in blood pressure. The details of that we'll learn later. Drop in blood pressure, kidney detects it. Kidney secretes renin. Now the renin is in the bloodstream. Turns out, increased renin, they call that number 5. The number 6, they show a picture of the liver. That brown organ over there. That kind of looks like a liver. Now the liver will secrete, number 6, a molecule called angiotensinogen. Now, it's renin's job to cleave angiotensinogen, which is inactive, by the way. It cleaves it to another molecule called angiotensin 1. So let's draw an arrow going from this. Renin is a cleaver. It cleaves. So renin cleaves angiotensinogen. it'll convert it to number 7, angiotensin 1. ANG1. So angiotensinogen becomes angiotensin 1. So ANG is an abbreviation. I'll write it out. Angiotensin. One is important, Roman numeral 1. Now, it turns out it will travel to the pulmonary capillaries, okay, number 7 and number 8. So it gets to the lungs. I'll just put number 8, lungs, the pulmonary capillaries. Now, in there, it's hard to see on the slide, I'm sitting in the back, that says ACE, ACE. There's an enzyme called ACE that'll convert angiotensin 1 to angiotensin 2. In fact, ACE stands for, I'll write it over here because I don't have room down there. ACE means angiotensin converting enzyme. So basically ACE will give you ANG1, converts it to ANG2. So let's pause here for a moment before I go on with the numbers. Go back one slide. This is why I put this slide in. And it's one of the things students struggle with. Renin is a cleaver. What did it do? It just took this angiotensinogen, a longer molecule, and just chopped the end off. Okay? And now what do we call it? ANG1. Then you went to the lungs. What did you do? You just chopped another end off, right? You converted it to angiotensin 2 in the lung. Angiotensin 2, that's the thing that'll do the physiology. So getting to angiotensin 2 is very important. So let's see what step we're on. We're on step 9 here. Let's go from 9 to 10, the adrenal cortex. So ANG2 is 9. Let's go to step 10. Adrenal cortex. So at the adrenal cortex, you release aldosterone, number 11. And then from number 11, you go to number 12, because what do you target? The kidney. You get the water and salt reabsorption. The sodium reabsorption and water follows. That's kind of what I said. Number 12 in lecture prior. So aldosterone targets the kidneys. You get the sodium reabsorption. H2O follows. Okay, then so from 12 we go to 13. That'll increase the blood volume. So that's 12. This is 13. Increase blood volume. However, I'll ignore the 16. I didn't really teach that. 10. This other one, 15. Angiotensin 2, in addition to releasing aldosterone from the adrenal cortex, it can actually directly vasoconstrict arterioles. That means you really clamp them down. That'll help keep systemic blood pressure high. Okay, so that's another way. So 15. So I'm writing vasoconstrict arterioles. Arterioles are the smallest of the arteries. Okay, well anyways, 15 and 13 are both ways to increase blood pressure. Two different ways shown there. I'll put 14. If I were numbering them, I'd have put that the last number. But anyways, boom, there, boom, increase BP. So there are two mechanisms of how the body can keep your blood pressure going in a stress response situation. Increase the blood volume or vasoconstrict, okay, until you correct this one. So I'm going to put a red, I'm going to ring it. Boom, that's what we did. And what we're trying to correct is this. That was the beginning, and that was the end. All right, so if I were you, I would commit that to memory. It might take some time. Well, it will take some time. But work on that. That's important physiology. This is one of the reasons why you sign up for 431. You learn about cardio, but even we see other systems are designed to help us maintain or increase blood pressure, a vital sign of life. In your clinical career, I'm sure you're going to measure blood pressure in your patients plenty of times. So now you know how the body regulates it. Okay, this slide you don't have to memorize, but I just want to plant the idea there. This whole RAS mechanism, it helps increase blood pressure in a stress response. A problem we have is some patients may be hypertense, blood pressure like a greater than or equal to 140/90. And so ACE inhibitors can help, because if we know ACE converts Ang1 into Ang2, what if you inhibit that? How does that affect this whole picture? Well, if you don't get that, this key molecule right here, Ang2 is the key to everything. Why? It does this and that, okay? I mean, you're going to get eventually a vasoconstriction, an increase in blood volume. So if you inhibit this release, or formation, I should say, you can help lower blood pressure, and that might help your patient. So that's kind of the answer to these questions here. I would kind of make a note to yourself. See if you can answer those later on your own. So before I move on to the next zone, any questions on what we're calling RAS?
Are we saying that Ang2 is both a trophic hormone if it encounters cortex, the cortex, and direct action if it goes to the...
I've never heard of Ang2 called a trophic hormone. You can think of it that way. It's controlling the release of this, yeah. But I've never seen it called that. But you're correct in your thinking. Any other questions? Okay. It's more the ACTH would be tropic to release this. But in this whole cascade, you're right. This does directly control the release of aldosterone. All right, the next zone, the sugar zone, salt sugar sex. Okay, I gave you one to know. And let's just talk about cortisol. I have some facts here that I thought were important about cortisol. So you're in a stress response over the long term. You want to regulate blood sugar. Okay, so if you're reading over that, cortisol is the most significant glucocorticoid. It's released in response to ACTH and also due to patterns of eating, activity, and stress. I think the key thing to know is this word here, the prime metabolic effect, gluconeogenesis. Let me write that on the board. You get glucose. The key thing is there's neo. You make new carbohydrates. So in this process, cells will have an ability to make carb from non-carb. You get the formation of glucose from fats and proteins. Okay? Now, the normal way the body will increase the glucose levels is to tap your glycogen stores. However, in the stress response, you want to spare glycogen. You don't want to use that up because in the brain, only glucose can cross the blood-brain barrier. Fats or proteins can't. So it's the only fuel source for the brain. And in a stress response, you want to spare glycogen. 1, 2. Spare glycogen. In a stress response. So maybe you have some glycogen, maybe it isn't completely tapped out, but if the gluconeogenesis is happening, you're getting glucose from other sources. That's why it's considered new. You're sparing your carb stores, your glycogen, and you're getting it from other sources. And in doing so, when you spare your glycogen, it's like you're saving glucose for the brain. That term is also used. I've seen it in your books. By sparing glycogen, you just kind of save glucose for the brain. Think of glycogen as like, I don't know, checking and savings. Money. Glycogen's your savings account. You don't really want to use that, do you? You want to save it for like, I don't know, maybe you're saving it for a down payment on something, for emergencies, you know, something like that. You don't want to use your savings unless you have to, some kind of emergency. And you just want to spend money in your checking, okay? Just drain it to zero every month, right? If you're like me. But this is like putting more money in your checking account. Oh, I got a retro check from work. But hey, what a surprise. You're getting your carb from somewhere else. Okay, and you're saving your savings account. Right? You don't want to use that. Once you tap that out and your brain has nothing to burn, I mean, I guess you have to do this. The thing about protein is, if your body is breaking down protein, you are starving to death. There's no doubt. Okay. So that's a remarkable stress response. Save glucose for the brain. Any questions on gluconeogenesis? It's an important term. Let's throw another term up here. Put a red line here. Cortisol does gluconeogenesis, but contrast that with glycogenolysis. That's simply, when you see that term, it's just break down glycogen. Which you normally do, okay, when you're not in a stress response. But this one, you're trying to spare it, okay? So don't confuse gluconeogenesis with glycogenolysis. They both increase glucose levels, right? And so you have pictures in the book. They're hard to teach from, but I thought I'd include them in my PowerPoint. Just look at it yourself. This is showing you the short-term stress response. I mean, what is man doing?
Running.
But he's not just running. What's he running from? Yeah, okay, that'll get your blood pumping. So, I mean, that's the physiology right there. Okay, epi and norepi in the bloodstream, your heart rate's up. If you're in Fitbit, I guess you can monitor it. here's the long-term stress. Okay, so they show, man, you got kicked out or something, you're just out in exposed, okay, overnight, for days, who knows. And so they show the situation. The physiology I taught today was right here. Pretty much, I gave you two to know. The aldosterone and the cortisol, those two. So here's the physiology. There's the ACTH. That says glucocorticoids, that's the cortisol. The mineralocorticoids, that's the aldosterone. That's why they show the renal effects there. And here they show the metabolic effects of the cortisol. The thing I told you to know is the gluconeogenesis there. Right, so those are good figures to help you review the adrenal cortex. I do want to move on to the next gland. For Zona Reticularis, I already mentioned they secreted the sex hormones, and that's all you need to know. Okay, they may contribute to other things, but you're not responsible for it. And so take some time to study the adrenal gland. I put some practice questions there. I don't want to take the time to answer them now because I'm kind of running out of time. But let me give you the answers. So when you go back and study, you can kind of quiz yourself. Let me see if I can answer my own questions here. Which of the following is not a stimulus for aldosterone release? Okay, that's good. Yeah, that does it. Okay, B is correct. B is not a stimulus. Number 2, which of the following is not an adrenal cortex secretion? That is. Oh, D is correct. Yeah, E is not correct. So D for number 2. Renin's released. A is correct for number 3. And then the RAS mechanism, which does not participate. So boom, 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 boom. All of them participate. E is correct for 4. So you got the answers. Go home and don't let yourself forget. Study, do your first review after class if you can. But let's move on to the gonads. Then I'm going to do the testes after the ovaries. So we have ovaries and testes. I'll do ovaries first. Now, we just have a picture of an ovary. They're inside the pelvic cavity in females. Okay? In males, they're outside the abdominal cavity in the scrotum. Well, anyways, here's a picture of the female reproductive tract. And we're not learning the whole thing here, but I did mention uterus before. What happens is you ovulate, well, an egg. I don't like that term, but it's a cell that's fertilized by the sperm. The proper term is oocyte. I'll write that on the board later. It's ovulated into this green structure called the uterine tube, where it can wait for fertilization. It can hang out there for about a day. And it happens one time per cycle, so about one per month. So basically you have about a 3-day window to fertilize that egg. The reason why we talk about this in endocrine is because the female hormones, estrogen and progesterone, are secreted from these follicle structures in the ovary. So if you cut the ovary open and kind of look at the follicle structures inside, over a 28-day cycle in a sexually mature female, we get all these different follicle structures with the egg inside, or the oocyte. And that's kind of what I want to talk about, because the mature follicles secrete estrogen. And on your histology quiz, you are expected to identify different types of follicles. So we have to go all the way back to before a female is even born, because that's when this story begins. So the ovary, think about the eggs or the oocytes. Those are the cells that undergo meiosis. They have half the genetic material of the person, and the other half is provided by the sperm. Okay, we'll get into that later. But anyways, the oocytes, they're surrounded by follicle cells, but during pregnancy, they're called oogonium. They're not even called oocytes yet. They're oogonium. They just undergo mitosis. follicles have not even developed yet. Undergo mitosis. I'm trying, right? So basically, egg divides in two, one becomes two, two becomes four, four becomes eight. You're just trying to multiply during the pregnancy. Now, at about the 7th month of pregnancy, before a female is even born, you have follicle formation. They're called primordial follicles. These are the most immature follicles that form. So basically, if you have an egg with a nucleus, and it becomes surrounded by follicle cells, so I'll use a different color for some contrast. The cells are usually flat-shaped. So there are many cells, many flat follicle cells that surround the oocyte inside. Okay, so if you're surrounded by squamous cells, that would be a primordial follicle. A follicle structure is, I think of a jelly donut. When you eat a jelly donut, you expect something inside, right? The jelly. And you'd be very disappointed if it wasn't there. In a follicle, you got something inside. In this case, it's the egg, the oocyte. All right. Now, once you form a follicle around all the eggs, you arrest mitosis. So that's it. However many follicles you got, or how many eggs you got, you're not getting any more. Okay. It's about 1 to 2 million. So by the time a female is born, at birth, you expect something like 1 to 2 million primordial follicles. However, these follicles are immature. They don't secrete estrogen. Okay? But you're not going to get any more. And there's just going to be attrition. They're just going to kind of die off as you go through life. Newborn obviously is not sexually mature. You got to wait till puberty, right? About 12 and a half years for a female. Average age for puberty onset. In the slide, look for the smallest follicles. And I'll point to them. Right? Like there or there. Those would be considered, well, they call them primary. I call them primordial. Let me define primary next. So anyways, I would look for them at the edge. The more mature follicles tend to get pushed in the middle where the blood is. Okay, and the more immature follicles hang out in the cortex region of the oocyte. The goal is, the reason why I'm teaching this, where are we going? Okay, we just got born. The goal is here, become sexually mature and ovulate once a month. So you're sexually reproductive, okay? And also, along the way, when we get more mature follicles, we're gonna get estrogen. All right, so we go from birth, you got about 1 to 2 million of primordial follicles, and then at puberty, fast forward 12 and a half years on average, I have a 13-year-old daughter, so I just went through this. Mom handled it, the first time. Well, anyways, you'll start getting your regular cycle, or your regular 28-day cycle. So each menstrual cycle, you'll select a cohort of about 20 primordial follicles to mature. However, by the time 12 and a half years later, you're down to something like 400,000. 400,000 primordial little cells surrounded by squamous cells. They're flat, they're very small, and they're on the edge. All right. So at puberty, when you start to cycle, select a cohort, a group of about 20 follicles, to undergo further maturation so you can have ovulation, right? A cycle is about 28 days, and at about day 14 of a 28-day cycle, you ovulate. So you have to kind of develop the follicles and all that time, and so you go from primordial to primary. The difference is in structure. I guess I can also draw this. If you have an oocyte, it's surrounded by cuboidal cells. One row of cuboidal cells. They're not flat, they're cuboidal. That will be primary. However, this is still considered immature. Not enough structure in this follicle to secrete estrogen. All right, so, but the next stage of development in the cycle, once you hit puberty, is secondary follicle. It's more difficult to draw. I'll give it a go. Secondary follicles, the oocyte is surrounded by many layers of follicle cells. And when they become stratified, you start to call them granulosa cells. Here's a picture of one here. That's a secondary follicle. You've got these little pockets of fluid starting to form. Little pocket of fluid. Little pocket of fluid. You have just many layers of follicle cells. So all of these cells that surround the one cell inside, again, they're called granulosa cells. They used to be one layer, but now there's many of them. And that's important to note. And we'll look at other slides. The other thing you'll notice is surrounding the granulosa cells, also part of the follicle, are these other cells. They look more fibrous. I'm using the color blue to illustrate these cells, but I'm just drawing them as lines. Well, anyways, those are called fecal cells. And the fecal cells, okay, the secondary follicle, when you get about 20 of them, okay, when you get your cohort of 20 and they develop to this stage, this is the more mature follicle, and you'll get the secretion of steroid hormone. So what will happen is, oh, and by the way, I should have mentioned this. Follicle development is driven by FSH, the follicle stimulating hormone. I can mention it here too. Let me just throw it up here. Under the influence of FSH, it'll help the formation of the follicle, but in particular, what will happen is fecal cells are important. They secrete that, for example, androstenedione. Now that's a male sex hormone. Now we want to convert it to the female. So what happens is that will be transferred to the granulosa cells. under the influence of FSH, you'll increase that aromatase activity. Under FSH influence, increase aromatase activity. You will convert androstenedione to estrone. Okay, so let me just kind of write that. Estrone is one of the estrogens. So from a secondary follicle, maybe you have a cohort of 20, one achieves dominance each cycle. Okay, so like in this picture, that's this one here. So you got many of these. One will become that. It's probably the one with the most FSH receptors. One follicle achieves dominance. Graafian. 2 A's. Now, the Graafian follicle goes by different names, maybe tertiary or vesicular follicle. I tend just to call it Graafian. I won't try to draw it, but it's easy to identify because it's the largest one. And if you look at this figure, it's the one where you have this moon-shaped fluid-filled pocket. They call it antrum, A-N-T-R-U-M, but there's the egg. Here's all the granulosa cells. And it also has the theca granulosa cell thing happening. But you first see theca granulosa on secondary. But here it is shown on, well, I labeled it, shown on a Graafian. Okay. Well, the terms are up there. You can see that, and basically, you can see the relative size. In this picture, if I had you to identify the stage of follicular development, we could do it together. What do you think one is? At the edge. These are all the primordials, very good. What about 2? Primary. I see one layer of cuboidal cells. Look at the relative size. A little bigger than those. And then you start to get bigger, like 3. Or that 3, or that 3. I'll call all of those secondary. And then you got the big boy here, that's, or the big girl, that's the Graafian. And that's the ovary. Any questions on the follicular development in the ovary? So now we know where the estrogen comes from. Yeah?
So you're saying at birth, like us as females, like we have the 1 to 2 million primordial follicles, and
That's
when
right.
we start menstrual, that's when we start getting rid of all of them?
Yeah.
Okay.
Yeah, you'll select a cohort of 20 each time. And if you did the math, that you still run out by the time you hit menopause. Menopause is about age 50.5, if you're reading textbooks. That's pretty much when the ovary is depleted of all the follicles, all the eggs.
So we're not making these though before menstrual, like we just have a whole bunch of primordial?
Yeah, they all form before birth. Once you form the follicles, you can't make any more. It stopped at before you were born. Female was born.
I mean, so we constantly have all the primordials, but are we making it
Yes.
Graafian before menstrual or no?
No.
No.
It only happens in a sexually mature female after puberty.
Okay.
Yeah. And so you got your bank of about 400,000 at puberty, and each 28 days you're selecting about 20 to develop. Yeah. So you got 20 less each cycle. I mean, 1 ovulates. Now you got 2 ovaries. My understanding is they take turns. The ovaries take turns ovulating. I'm not sure how or why. Okay, yeah, no problem. All right, here's the testes, and I'll be really quick about it. Well, here's a picture of the testes. If you were to cut it open, well, the structures that make the sperm, spermatocytes, seminiferous tubules, and well, I guess we'll talk more about that in repro. Thing about it is, when you make a histology slide and you were to cut a bunch of tubes, you'd see a bunch of cut tubes. And that's kind of what you see here in this picture. But if you look in between the cut tubes, there's these clusters of cells in the interstitium, so they call them interstitial cells. They're the cells outside the seminiferous tubules. These cells produce the testosterone. So you got the testes. You have all these compartments, these little partitions, and each of those has maybe several with very long seminiferous tubules. Now, a big long tube is very convoluted, but if you were to cut it, okay, and that's what you're looking at in the PowerPoint slide. You have all these like cut tubes, seminiferous tubules, where the spermatogenesis occurs. In endocrine, we're concerned with the cells that secrete the testosterone. And they would exist outside the seminiferous tubules in the interstitium. So a bunch of little cells outside there. Interstitial. Sometimes they're called the interstitial cells of Leydig. It's an older term that I still use from time to time, so Leydig. And anyways, I point to blood vessel because hormones need to get into the bloodstream, right? So you expect to see a blood vessel close by. So we got estrogen for females and testosterone for males. Turns out the interstitial cells in males, that's like the theca in females. We call it the homologous structure. Now I think this is a good place to shift gears. I can cover thyroid, parathyroid starting on Friday. But right now I want to make sure I have enough time to teach the histology slides so you're prepared for Friday's histology quiz. So let's take like a 5-minute stretch break. You don't have to leave the room if you don't want to. I won't lock the door. That'll give me some time to get the slides so I can present them to you.